Welcome. We've got a few things like primitive data types. Primitive data is pretty much everything. There are certain data types that we work with all the time on a hierarchy. So we're going to talk about the primitive data type hierarchy. Actually, you know what? We might want to actually start with that. Let's see. Data conversion is a big part of it. Of the data types being, and of course, where are those variables, and assigning those variables? Where are they located? They're in RAM, of course, but what do we call that? Let's start with where the data actually, because I don't want to get so bogged down in this stuff, but I also don't want to lose it with let's actually play catch up on this primitive data types, because let's show that. Okay. Because we're going to be talking about converting today quite a bit. And there is a hierarchy of data. But first, where's those primitive data types come from? Because we've talked about everything's being a number, and everything that we work with in software for computation first is put into RAM. That's then loaded onto the CPU. So the data types that we have at a low level, and that means that any software, that or development kit has the ability to use these common data types. But remember, everything's a number. So at the bottom, I put the char. And guys, I am using synonymous code with C-style coding. So this is all these data types are C-style code, like C#, Java, JavaScript, PHP, C, C++. All of those are C-based languages. Python, no, but I mean it's still C. So whatever, it's shorthand C. So all these variables are pretty they're pretty much seen across all integrated development environments. So char, I put it, of course, byte down here would be, but this is all preference based. This is my idea of the hierarchy of the data types. So char, I put it at the bottom as 1 byte. That's the char is what holds one single character. So it would be like an A, a capital A or whatever, and it's 1 byte. And notice the single quotes I'm using. That's how we use it literally in programming. Then I would put like the short int, but we could just shorten that to int. I love that. Shorten that to int. Integer, that's 4 bytes. That's just a normal number, 1, 2, and it's considered also unsigned, so it's -1, 1, 2. And then we have our float. Our float is the decimal. You can have decimal points in it. Excuse me, it's 4 bytes, and I'm giving you the example in the wrong column. Oh my goodness. Okay, so it can have decimal points in it, like 4.4, 4.3, that sort of thing. That's what a float is, and it's 4 bytes. My scribbles are already getting to be a nightmare. Oh my goodness. All right, and then we got a double. So we're going to be able to wipe this one quick. Double is 8 bytes. A double is 8 bytes. And I started out so well today on this thing. Whatever. All right, I'm done with that. So as you go up and down this chain of the double, the float, you go through these conversions: the integer, the char. Uh, these can all be interchangeable and be converted from one to the other. And if we convert a char to an integer, that's a graduation. If we convert an integer to a float, that's also a graduation. But also, it's kind of a degraduation because now that it's a floating point, it can't hold as large as a value of numbers. The range of numbers reduces, and then of course the double and all kinds of different variants in between. But these are the four general types. I don't put string at the primitive data type level. String is an object that's composed of multiple chars inside of an array. Multiple of these guys right there. And those primitive data types are what everything is and comes down to at one point or another. Even the pixel on your screen is just a series of numbers. So data conversions are pretty much a problem because if you go from a int or a floating point to an integer, that creates a precision issue because, well, not precision issue, but a truncation, a data loss issue, because data is truncated when a conversion happens with a float data type to an integer. What do I mean by conversions? Let's get a little bit more explicit. So let's say I create an int called, let's do this, alt plus integer called I, and a float called j, and I assign j to 4.5. Well, if I take I and I assign it to j, what kind of problems can happen? Well, first off, we got to spell the variable right. Because remember, if I'm doing an assignment, that's a process that goes on the processor. Or actually, no, excuse me, no, it's not. This is where we control where we control, because we don't allow different data types to go on a processor. We need to control how conversions are made. And in this case, we could have an error. Let's see what we get. I'm just going to clean and rebuild. Just use the hammer and the broom. Okay, error. So it definitely does not like some of this stuff. Oh, well, duh. Okay, let's see where I'm going. Probably wouldn't like that conversion. Let's see where it is. Yeah, right here. Incompatible types, possible loss from double to float. And the reason being is because that 0.5 just gets truncated and I just becomes 4. The integer I just becomes 4, and that's it. 0.5 is gone. So now that value that I had in j, even though I is now been assigned to it, I is an integer. It can't hold that 0.5. So it gets truncated. And so that's a whole 0.5. So let's say that that's a money conversion. And that's $4.50. And you're losing 50 cents every charge or whatever. That's there's real consequences for computation, and that goes double for banking computation between different floating point values with decimal precisions. How far out does the decimal point go? Because there's been banking algorithms where they make money from fractions of a cent between divisions, or whatever, the mathematics that go on behind the scenes in the math or the banking world. So that's the issue with primitive data types is, and with your expressions that we're going to be exploring, is because data types cannot be processed, different data types cannot be processed, when we take different types of data and add them, subtract them, multiply them, they have to either be graduated or degraduated to be loaded onto the CPU for processing, so that they're both the same type. One way or the other, down or up. And we got consequences both ways. Some languages will allow a conversion implicitly, meaning it won't make you have to do it. Some won't. But let's talk about the stack and the heap, because memory goes. Memory, when you declare it, comes from the stack, and that's automated memory that is given to your process. So, given your RAM, whatever RAM you have, let's say that your RAM is 200 bytes. That's how much RAM that you have, 200 bytes. So that means that addresses 0 to 199 have the ability to be filled with data. And when I say addresses, I'm just saying byte locations within that 0 to 199. So think of those byte locations as house addresses or something like that. Now, when your process starts up, and not the middle language process, the interpreter starts up. The interpreter, the low byte language, middle language of Java starts up. It asks the operating system, or it's given automated or automatic memory from the operating system as part of the process, and that's part of the tool chain that's given to us through the integrated development environment. And that memory we call automatic memory. And when we define a variable, like we just here, or declared, not defined, declared, that 4 bytes is used and put on the stack. So when this line is processed, that memory goes on the stack that is given to you. And so you've got those 2 types of memory. The stack and then the heap. Now the heap, you have to ask for memory. That's you use the new operator within Java to do that, and you guys will be doing that. You probably already have, actually. And then the stack is the memory that's automated, and therefore you have the ability to blow the stack. That means that you can create so many variables that are added onto the stack that you overrun the stack. Or you run a function so many times within itself, it blows the stack. And we call that a stack overfill. Or stack overfill. So those errors happen, and there's actually, what is that website? Stack Overfill, Stack Overload, Stack Overfill. Is this Stack Overload? Stack Overload. Yeah, Stack Overload, isn't it? Yeah, Stack Overload. Let's see. Stack Overload. Stack Overflow. Yeah, okay, Overflow. Yeah. Stack Overflow. And Stack Overflow is fairly common to happen when you're doing fairly complex tasks and you're really taxing the memory to its limit that's given to your process. And that means you've got a lot of lines of code, you're calling a lot of functions, you got a lot going on. So every time that this program runs, when we set a breakpoint, these variables go on the stack. And then when the program gets done running, when your runtime gets down here, these variables come off the stack automatically. And we call those automatic variables. And of course, we can examine those in the debug mode. And so forth. So let's see. Why are you being a stinker? Okay. Well, anyways, let's go back to some PowerPoint and we will go from there and continue on. So I talked about data types, conversion, loss. It's always okay to graduate. Here's a literal string, and we can create a string. And notice I've defined a variable that I've given a name. Oh, before I move much further, let's back up real quick. To go up and down explicitly the hierarchy of data types, you use casting techniques, and this is most C-based languages allow it. You will tell J, since J is a floating point, and the compiler is saying, or the interpreter is saying, hey, you're losing data here. This is a big problem. You can say, no, I really mean that. I want you to convert this to an integer. And then assign it to the integer. And let's see how well this does. Oh, silly goose. What am I doing here? I'm using J way too much. All right. Where are you? There you are. Another thing that Java will complain about is when we use literals, because this is a literal string that I'm literally typing in. This is a literal float that I'm literally typing in. But when we do it this way in C-based languages, we're actually meaning a double. This would work without any yelling. Here we got to say, oh, that's not a double, that's a 4-byte float. And then Java's nice and happy, and most C-based languages like that. And we don't need to use the double, inefficient, but hey, we got enough RAM now where it's not even an issue anymore, really. So most people just use the double by default now for precision. Okay. So notice this cast, how I convert J to an integer. This works with graduation as well. We can say J, let's convert J. Let's actually, you know what? Sometimes they will just allow graduation implicitly. Let's see how Java does. Yeah, Java does not like that as well. All right. So we will do this. float and make an explicit conversion. And then let's rebuild it. Oh, it doesn't like it because it's not initialized. Okay, yeah, all right, fine. But that's the idea. Graduating with typecasting, either up or down the hierarchy chain. And this is pivotal to getting all your expressions and your mathematics right, that an understanding and awareness of this is made. That's why I'm focusing so much time on it. Because when we get into actually mixed expressions, that means when we're taking, and when I say mixed expressions, that's when we're taking an integer and adding a float to it and dividing by a double. What happens? How is that working when it finally gets loaded onto the CPU? Because we're taking an integer, adding a float, and dividing by double. What the heck is going on up and down that chain of the hierarchy with the conversions as it gets loaded onto the CPU? And that can get tricky. That's where a lot of whole languages have been built to solve that problem. Python was built to solve that problem. Okay. TypeScript is another good one. That one's more modern. Oh, don't want news today. And one last thing before we move on in the PowerPoints, I want to show you the call stack. You can only look at it in debug mode, so you have to actually set a breakpoint, run up here in debug mode, run debug project, and when you get into debug mode, then you can view the call stack and see what's going on kind of behind the scenes with your RAM that's automated, your automated RAM. So all function calls also go on the call stack, as well as variable declarations. And you can go to the call stack by go to the window, debugging, but you have to be in debugging mode, window, and you're going to go to debugging, and then there's call stack here. You see how you got all this other stuff. And then you can even manage threads, multi-threading applications. It looks like, apparently. I haven't done that. I haven't done multi-threading with this one, with NetBeans. But so we add the call stack, and you can see what's going on. So let's see what's going to happen in the call stack right here. Let's see how well NetBeans did the call stack. It looks like they're just doing it line by line, but eventually when we do function calls, you're going to be able to see a little bit more of what's going on behind the scenes within the call stack. But definitely look into that window and different debug modes and things that you can see just as you're working through and learning learning to debug actually. So that I use the call stack view quite a bit in programming because I need to see what functions have been called in a series down the tool chain to get an idea of where I'm at when I'm debugging. The call stack is something that you're not going to need to get too crazy in for a while, but be aware of it. All right, what else we got going on? System out for printing, good. We kind of talked about that. Here's some output, string concatenation. That one is part of the operator. It's time to get into expressions. So let's get into expressions. That was the big thing. We talked about conversions and casting, but that none of that really comes into clarity. We need to definitely get into that clarity unless we put it in context with a line of code that we call a statement or an expression. And let's bite off a mixed expression right off the bat, so that we can talk about data conversions, and then we'll kind of pop back into that. I want to get into that particular part of it. We can do operations on our data types. String concatenation is an example, but how do expressions actually work? And for that, you're going to want to go to, in any language, it doesn't matter, it's all the same. Operator precedence and associativity. This is kind of the main, one of the other big ideas for this chapter is stack, variable conversions, and then mixed expressions. I think that's quite a bit. We'll do some demo modeling, of course, in another video. So operator precedence and associativity are the rules of the different types of CPU activities for processing you can have with the different data types. And what happens first? You learned it in middle school. You learned it in middle school. You did. What happens first on a line? Plus or multiplication? What happens first? Plus, minus, or divide? So that's just order of operations. And we learned already naturally left to right associativity. If there is a... Okay, let's get in context, because I'm talking without concrete examples. Let's go with a mixed expression. What we're going to do is we're going to go with a mixed expression. Let's just say now I can do a literal, I think it's just 3.4 there, and Java won't lie. Hopefully I'm not lying to you. Okay, yeah. So it'll take the double just direct with the literal instead of having to put the F for float. Okay, I'm going to change these names so that we can refer to them a little bit. FLT, STR, good, good, good. And then CH. You know what? We're not going to play with this one. Char. CH. And then N. And number. That works. Okay. So let's say the 6, 5, whatever, and then we're going to have a integer called sum. Okay, now let's. So this is going to be a mixed expression. Now you notice how I use single quotes there for char. And let's do this. Let's say that sum is equal to, now we're on the operator precedence, operator precedence and associativity chart. We're going to be working with these different operators. This is not a good chart. Charts are, it's a little bit better. Table. There we go. So essentially, if we have a statement or an expression, it's saying that anything that determines what expression or what part of the statement is loaded onto the CPU first. Which one? Is it going to be plus, minus, divide, etc.? So let's get a little nutty here. And one other thing, we got to add the modulus. We got to do modulus. You know, modulus. We might just put modulus to the demo for this week. Okay. So let's give you an example of left to right associativity in this as well. So we're going to say sum is equal to number plus number minus dBl divided by let's go nutty. Oh yeah, let's divide it by a character. Okay. And then let's multiply that minus, plus, okay, I'm going too nutty. Okay, let's just do that by, divide it by FLT. And, I think that's enough for now, except for this last one. Times 3.2. All right. Then we're going to do this. Minus CH. All right. We're taking a number, adding it together. Integer plus integer minus a double, divided by a floating point, multiplied by 3.2 minus CH. What happens first? Operator, precedence, and associativity say, well, on the table, if we look at the table, what happens first is multiplication before addition. But multiplication and division are on the same hierarchy. Oh, but then we do the one that's leftmost. That's left to right associativity. So we know that the plus minus doesn't happen. This minus doesn't happen yet. It's either these two that happen first. And I'm talking about when this line of code evaluates. What is it going to print? What is it going to print? Let's put this in debug mode. Oh, we can't get it to compile yet. We're going to get to compile. We will. We got to convert the CH. I'm pretty sure we got to do a bunch of conversions. So right now, let's just try to get an idea of what it does not like. Possible from double to int. All these different conversion problems. All right. Well, here's the problem. I'm assigning an integer to the addition of, or the subtraction of two doubles. This is a problem. It does not like any of that. So what do I have to do? Well, we could decide that since this division happens first, that we need to convert this just to get it to compile, have this happen first, and then convert that to an integer. Then we'll multiply it by 3.2, Let's just have it truncate that. And let's see if we can get that compiled. And then, oh, how do we convert a char from, so let's just, hey, how do we convert a char to an integer? So you see the kind of conversion, since and then I, as a programmer, have to decide where in the expression these conversions happen. And that's part of the computer science of it. And it gets rather complex. So let's see how this evaluates out. We're going to continue on with it. Let's work with this getting it compiled first, and then we'll talk about order of operations. And we'll have to convert this ch to an integer. And what it does is it just takes the char, the capital A here, and if we go and look at the ASCII code chart, where is the ASCII code chart? We see that the capital A is a 65. So just like any C-based language, we cast that to CH. So let's see what it does now, if it's going to yell at us too much and where we can get it. Oh, hey, it likes me now. Okay. And as, does it really like me? Because it's just not liking that. Let's see. Is it going to actually do it? No, yeah. Okay, let's do this. I'm in run mode. I wanted my IntelliSense to pop up because I'm lazy. And it'll convert that to a string for me. It should, and output it. It might not. We'll see. Yeah, okay. It'll be fine. Okay. All right. We are going to do this in debug mode and look at it. Okay, so now we're running numbers 5. We got the call stack up. We're not really running functions, so that doesn't matter too much. We'll look at our variables. Doubles 3.4. Number. Okay. All right. Good. Now what does it do first? Well, first, and let's break this down. Why aren't you going smaller for me? I wanted to get my whiteboard up, but I think, okay, yeah, that'll work. This will work. What's going to end up happening is the operator precedence and associativity is going to be followed here. But first, we need to consider the operators that have been added that we haven't really talked about or looked at, and that is these parentheses that I've added here and here to make this compile. And if we look at operator precedence and associativity, where are you at? I had you here. Do you see how high the precedence of parentheses are? So whatever you put in parentheses is going to happen before any of this kind of processing, or for that matter, any of these, for an expression, or a statement. Mixed expression, mixed. This is the rules that are followed. So what happens first is that DBL and FLT are divided. Well, what happens there? Well, let's say add watch, and let's look at what it returns. It returns dBl divided by FLT that happens first, it returns 0.75. So we've got this guy right here goes to a temporary variable that is got the value 0.75. All right, that happens. Then the next thing that happens, if we look at operator precedence and associativity, casting happens first. I don't think they show typecasting here. But casting is going to happen next. So you know what that 0.75 is going to turn into? 0. Yep. Okay, now, then we take that 0, we multiply it by 3.2, but that integer conversion happens first. Multiplication doesn't happen next. We just got the 0 from all that other stuff that we had right there. That all evaluated to 0. So what's the next operation? Well, operator precedence says, oh, we got to convert that. That becomes a 3. Oh, and notice I'm doing left to right here. That's pretty much standard behavior for associativity on how things are evaluated. Top down, left to right. Always, guys. Top down, left to right is your mechanics. So here's CH. We got that converting to an integer. And if we look at the ASCII code chart of, well, what is the value of CH? Capital A. Well, what is that capital A? Capital A is going to be 65. Okay. So that's going to come in at 65. All right. Now we've got number times number, or number plus number. So that's going to be, oh, but wait, what happens first? That doesn't happen first. That doesn't happen next. Because we still got this multiplication, don't we? So 0 times 3 gives us a 0 here. Then we got number plus number. Because these are all on the same hierarchy. So their associativity, yeah, I have a problem with that one, is evaluated left to right. So it's going to be now this that gets done. And so that's going to become 10. And this is all behind the scenes in a temporary variable that is on the stack. That's all this is being loaded onto the CPU and happening without, as it's progressing through the instructions that are given to it. Now we got 10 minus 0 is 10 minus 65. So sum should be negative 55. Now guys, I could have gotten this whole thing wrong. I don't know. We're going to find out. Sometimes I get it wrong. But we're not gonna do a deep dive if I get it wrong. We're just gonna, hey, I'm giving you the rundown somewhere I messed up. Let's see where. Let's see. Sum. What are you, sum? Come on, give me some love. Negative 55. Thank you. Oh, thank you. Everything's a number, guys. Everything's a number. Everything's. It's so stupid simple programming and numbers that it's difficult because you got to do complex things with simplicity. And the more you're into that simplicity and getting complex steps out of simplicity, the more you understand computer science. through, we've talked about the stack, automatic variables, defining variables, primitive data types, conversions, casting. Let's hit the PowerPoint real quick and do a flash by. Oh, right there. I knew. Yep, I knew we were getting too fast and loose. Okay, we're gonna. Yeah, let's dive in a little bit more here. These are common characters that we work with for outputs and inputs for text-based formatting, and also console input and output. You can inject console new lines because everything in the console and text files is done through the ASCII code. So these are direct special characters that directly relate to how the ASCII is rendered on the page. Like the tab, the new line, and so forth. Essentially, mostly the tab and the new line. I use a lot. The carriage return is mostly for DOS systems. And also, the thing is if, we're using a language that has special characters. When you are using a language that's based on the characters and you want to output the characters themselves that are used for special formatting, so let's say that you want to print a double quote. How would you do that? How would you print a double quote? Because we use a double quote to tell the print function what characters, or we use it to represent a string, which is what the print function expects. So the very structure of our language, if I want it to print this, but I want to have a double quote in it, you see, like I want to print a double quote. I want to show a double print. Print this double quote. And the thing is because the double quote is part of the language itself, you've got to tell the interpreter or the middle language that, hey, this is actually a double quote that I want to print. So you use a special escape character, the backslash, and you say, no, I really mean a double quote. And then what it'll do is, this is my special formatting that's being a bit of a poor master here. Let's see. It's the automated. So even this auto netbeans thing is not allowing me to put in a double quote. So the language, the IDE itself is killing me. So I don't know. I might have to break this stupid algorithm that's not allowing me to print a double quote. Let's see how it does for a backslash. Here's another example. I would have to do some settings to do the double quote within the IDE, but the backslash is also a special formatter. So if you really want to print a backslash, you would put 2 backslashes. Like that. And then finish up your output, your instruction. So you're instructing the interpreter to print what's inside the double quotes. But what it's going to do here is it's only going to show a single backslash in the print. So let's look at that. Oh, it does do the double. That's interesting. Was it the backslash that was? Sometimes it's actually, let's see. Yeah, I was doing it backwards. Sometimes I actually do that. Yeah, excuse me. It's been one of those right there. Yeah. So it was that stupid auto thing fighting me on my double quote example that had me off on my backslashes. So this is the backslash formatter, not the one that I was showing you. That's a very common error. I still make it today, obviously. But let's look at what it outputs. So you see I've got 2 backslashes here, and we run it, and you see we only have 1 backslash as the output. We would have to do another backslash to get 2 of them. But what we're telling it is, hey, I'm not trying to print a new line here. I really mean I want you, because this is used for a new line as a formatter in text documents and input-output. So if we look at this output, we will see, you see where it's got the new line down here in the output. So a lot of what you'll do eventually is you'll be writing code, you'll be writing a program that writes a program. And that's when these escape sequences go a little nutty. But that's for injection, and we don't want to get into that topic for where we're headed and stuff. But everything's using that ASCII code chart. All right, let's see. Anything else that I see here? Good. I think I've hit the main expressions. Yeah, I got you. The meat. The only other thing is these guys right here for shortcuts on some common expressions that we have. Let's talk about that real quick and get into the modulus operator. So let's look at, let's see, arithmetic expressions. This one right here. We've already kind of looked into this and demoed it, but this one right here, this modulus, this is the programmer's best friend. And that's what I'm going to leave you with today. And let's talk about some of those shortcuts real quick. All right, some common things. In computer science, we do accumulations quite a bit with variables. So we'll start a variable at 0, and we will use that same variable to keep track of an occurrence of some kind. And we just iterate that occurrence by adding 1 to the number's previous value. So when this line runs, number is equal to 0 plus 1. So number becomes 1, and then this line has number where it's equal to 1. That's a pretty common thing that we call accumulator. So we've come up with various ways to shorthand that. So we could do number plus equals 1. That's synonymous with what we just had. And you can do it with the multiplication operators and so forth. And we call these accumulators because they are, this is the example of this, number times equals 1 is the same as number is equal to number times 1. We also have very short accumulators. That one, that will add after every other expression on the line is complete. So if there's another bit here where you're saying let's say like I is equal to 3 plus number or something like that. I is equal to 3 plus number. 3 plus number, 3 plus 3 plus number. 3 plus 3 would happen first before number was added to. But if you had the prefix, number would be iterated first before these guys would be added. So there's all kinds of different ways of doing that accumulation of variables. And you can change this to 5 so that it accumulates by numbers equal to number times 5. So you can do times equals 5. Like this. Oops, that's plus equals, same thing. Sort of like that. But the modulus operator is where I would like to spend some time on, because it is a programmer's best friend. And we get to go on Mr. Whiteboard for a little bit. All right. Let's put the modulus operator in context of the code. It would be like this. Okay, and let's just change this to x. We're not even going to run that line. I'm just going to do it in the debugger and show it to you through the debugger. All right. Let's do mod 3. Let's set the breakpoint right here to get rid of this one. So we start by assigning x equal to 0 and number is equal to, let's say, 4. There we go. All right. Modulus is the remainder of it. And this is the setup and how it looks like in code. And then we're going to get into the whiteboard. All right, so when I run this, we assign x to 0, number to 4. Then we say x is equal to 4 modulus 3. And what that means is it's the remainder of 4 divided by 3. That's the modulus operator, and it is your best friend. It solves a lot of problems with mathematically. So what is 4 divided by 3? It's 1. 3 goes into 4 once with a 1 remainder. So that's going to output 1. So x, you see it down here, is 1. Okay, so that's modulus. Now let's extend this a little bit and kind of look at it with a little bit more repetition. So we're saying x is equal to number. I'm just going to use n here. N modulus 3. Okay. So when n is a value, x is going to be another value. So if we assign 0 to n, what we're saying is, what is x 0 modulus 3? Or what is the remainder of x, or of 0 divided by 3? And since the modulus is integral only, it only deals with int, we get a little bit of some wacky stuff, but what it comes down to is, well, 0 divided by 3 is 0 with a 0 remainder. Now, what is 1 modulus 3? 1 modulus 3 is 1 the remainder of 1 divided by 3. Well, 1 divided by 3 is truncated to 0.33. So that's a 0 with a 1 remainder. Yeah, it's beautiful. So when n is 1, n modulus 3 is 1. Okay, when n is 2, so that means, what is the remainder of 2 divided by 3? Well, 2 divided by 3 truncates at 0.66. 666, whatever. And it goes down to 0 with a 2 remainder. Well, it's going to start kind of coming together here soon. So bear with me. This is about where it starts turning. What happens when we get to 3? Well, x, or the modulus of 3 divided by 3, well, that's 3 goes into 3 once, but it's got a 0 remainder. And 4, we already know 3 goes into 4 once with a 1 remainder. 5, what is 5? The remainder of 5 divided by 3. 3 goes into 5 once with a 2 remainder. 6, 3 goes into 6 twice with a 0 remainder. 7, 3 goes into 7 twice with a 1 remainder. 8, 3 goes into 8 twice with a 2 remainder. 9, 10. Oh, I messed up here. 10. Do you see the pattern? You can convert any number within a specific range using the modulus. That's how random takes a large number and shrinks it down to a smaller random number. You know, like for dice, 1 to 6, a random number 1 to 6. Random returns like huge numbers, and they got to be converted down into, you know, if you're using dice, it's got to be 1, 2, 3, 4, 5, 6, that sort of thing. Okay. This is modulus operator and how it works. You know, when you get to looping, you'll kind of get a better idea. But this is how accumulators work, and why we, you know, and kind of a glimpse into some of the use of this and how it will apply to repetition within a bound set of values or whatever. You know. All right, I think I hit most of the main key points that I wanted to. Let's see, stack, variables, expressions, conversions, casting, and then operator precedence, associativity, and then of course the modulus operator. All right, guys, I will see you next time. Thank you. Bye.